Hello and welcome back. So today we're going to be talking about how we name ionic and covalent compounds. So later on this year, we're going to talk way more in detail about ionic and covalent compounds. But right now, we just need to get the basics down and need to know how to name them and write their formulas. So first of all, I'm going to pause for a second on the naming, and we're going to look really quickly at how we classify matter, just so we know where ionic and covalent fit in. So matter is anything and everything that has mass and takes up space. So matter can either be in a constant composition, meaning any sample of that matter is going to be exactly the same when it comes to what atoms it's made of and their proportions, their ratios, or it can differ depending on the sample you get. So if that property or the composition is going to stay the same, we call that a pure substance. So in this class, when we talk about the word substance, we're talking about any type of element or compound. Okay, so substance is any element or compound. So pure substances broken down to elements and compounds depend on, is it as simple as it gets, or could it be chemically separated down? If it is as simple as it gets, then it's a pure element. If it can be chemically separated, then we call it a compound. Okay, so what I mean by that is water, H2O. It's made up of hydrogen and oxygen. I could, through a chemical process, separate that into hydrogen atoms and oxygen atoms. Therefore, water is a compound. But if I only had hydrogen, I can't break that down any further. That's as simple as it gets. And then in our compounds, we have two types. So we have ionic and we have molecular. We're going to go more into that. Quickly, if we don't have constant proportions or constant composition, we call that a mixture. So mixtures can either be uniform throughout, meaning they're exactly the same all the way through. So those are things like our solutions, for example. All right, those are called homogeneous because homo means same, so they're the same throughout. All right, so for this, think vanilla ice cream. And then if they're not constant throughout, we call them heterogeneous because hetero means different. So for that, I want you to think cookies and cream because you might get a bite of cookies and cream ice cream that has like half an Oreo in it, and that's a good bite. Or you might get a bite that just has like the little crumbs of Oreo. It's not consistent all the way throughout. Sand is another example of a heterogeneous mixture. All right. So now that we kind of know what these terms and names mean, let's look at how we name. First, we're looking at ionic compounds. So ionic compounds have the word ion in it. All right. So what that means is they're made up of ions. So they're made up of cations and anions. Anions are negative and cations are positive. So when we have a positive and a negative together, they're held together by their opposite charges. So ionic compounds might be made up of metals, which form positive charges, non-metal and a non-metal, which is a negative charge, or a polyatomic ion. Now, I will point out that there is one polyatomic ion that is positive. So that positive polyatomic ion would have to be with a negative polyatomic ion or a non-metal. Other than that, all of our ionic compounds are going to be a metal and then a non-metal or a polyatomic ion. So we use our periodic table for ionic compounds or the Roman numeral for their charge, and I'll explain that later in a minute. Ionic compounds have to be neutral. So what that means is the positive charge and the negative charge have to cancel out. They have to neutralize each other so that the whole compound itself doesn't have a charge. And in ionic compounds, atoms are either going to gain or lose electrons to become positive or negative as part of the ionic compound. So one other thing I want to point out with these polyatomic ions, like a refresher, they are treated as one thing. So they are one ion that's made up of multiple atoms, hence the name poly, many, atomic, many atoms. But we treat them as one entity. So the whole thing, the whole ion has one charge. So for example, if we look at SO3 2-, for example, that is sulfite. It's made up of a sulfur and 3 oxygens, but the whole ion has a 2 minus charge. All right, so we treat it like when we're balancing these and we're putting them into formulas, we treat it as one whole thing. So when we write the formula for an ionic compound, we're going to start by just writing the symbol for each ion. So we're going to start out simple with lithium bromide. So we're going to write down our two symbols. We look and we see that lithium is in group 1, so it has a +1 charge. Bromine is in group 7, so it has a -1 charge. And depending on who you had as a chemistry teacher, you might have looked at it a couple different ways. You might look to see, okay, so +1 and -1 adds up to 0. So we only need one of each, so I have LiBr. Or your teacher might have taught you that you can kind of crisscross the charges. And so 1 and 1 still gives me LiBr. However you want to look at it. All right, the next example we have calcium chloride. We wrote our two symbols, Ca and Cl. Calcium is in group 2, so it has a +2 charge. And then we have chlorine, which is in group 7, so it has a -1 charge. Now, this time we do not add up to 0. And so, again, you can either look here and you can see, all right, how do I make that equal 0? Well, I need 2 of these. Or you can look and say crisscross 2 and 1. So I need 1 calcium and I need 2 chlorines. Okay? Finally, Roman numeral tells me the charge, and we'll get into it in a second why we have Roman numerals. So if there's a Roman numeral, that tells me the charge, not the periodic table. So for iron, I know it is a +2 charge because the Roman numeral tells me that. Oxygen is in group 6, so it has a -2 charge. So 2 and 2, we have FeO. So how do we name ionic compounds? So we kind of have 3 sets of rules when it comes to naming ionic, or kind of 3 categories that we name differently. So the first is a binary compound, meaning it has 2 ions, and we're only going to be doing compounds with 2 ions, with monoatomic ions. And all that means is they're 1 atom, so we don't have any polyatomics. They have a metal with a constant charge, okay? So we have certain metals that their charge never changes, okay? They always have the same charge when they form ionic compounds or when they form ions. Group 1, which is always +1. We have group 2, which is always +2. And then we have 4 transition metals whose charges never change. So we have silver, which is always +1. Then we have zinc and cadmium, which is always +2. And then we have aluminum, which is always +3. Okay? So this first category means that you have 2 single atom ions, a metal that comes from one of the 2 groups or one of these 4, and a nonmetal. All you're going to do is you're going to name that metal, name the nonmetal, but you change the ending to "ide." This ending of "ide" signifies that we're in a compound. So if I just say sodium chlorine, well, in that case, I'm talking about solid sodium, which explodes in water, and chlorine gas, which is poisonous. But if I say sodium chloride, I'm talking about the compound NaCl, which is table salt. Okay? So NaCl, sodium chlorine, change the ending to "ide," sodium chloride. MgBr, magnesium bromide. All right, so we just change our endings to "ide." Super simple. Our second category, we still have a binary compound, but this time we have polyatomic ions. This is very simple. We just name the metal and then the polyatomic. Polyatomic ions already have their own endings, such as "ite" and "ate." So we don't need to change the ending because they already have their own ending. The only tricky part about this is you've got to memorize the polyatomic ions, okay? And I've got to practice for you to do that. So here, sodium bicarbonate. Don't change the ending. It already has its own. Potassium nitrate. Cool? And then our last category is when we have metals whose charges change. So these are our transition metals, except for the ones we mentioned before whose charges stay the same. And so I like to think of this like if you have Joe Smith and he's a senior and then he has a son, Joe Smith Jr. Okay? So if I just say Joe Smith, I don't know if I'm talking about senior or junior. So I have to specifically specify Joe Smith Sr. or Joe Smith Jr. These charges for these metals are the same way. Because they can change, then we have to specify which charge this ion has, in this case, with a Roman numeral. All right? So if I have iron 3 sulfide, that 3 in the Roman numeral tells me that iron has a +3 charge. Now, if I'm just given the formula, how do I figure that out? Remember, non-metals don't change their charge. So I'm going to start there, okay? So sulfur is over here in group 6. So sulfur has a -2 charge. Well, I have 3 sulfurs, so in total, I have a -6 charge. Well, I only have 2 irons, so in order to balance this out, each of them would need to have a +3, which is where I get the Roman numeral 3. In the bottom one, I have chlorine, which is -1. I have 2 of them, so I have a total of -2. I only have 1 copper, so it has to be +2, which is where we get the name copper 2 fluoride. All right, so here's some practice of giving you the formula and you need to write the name, or giving you the name and you need to write the formula. What I would suggest is that you pause the video, try it on your own sheet of paper, and then play it so you can see the answers. All right, so here are your answers. Okay, so most of these are pretty straightforward. The biggest thing we see is that we've got to memorize our polyatomic ions to know their names. We notice that for manganese and mercury and chromium, we had to use Roman numerals because they were transition metals whose charges did not stay constant or do not stay constant. And then down here for these two, we used the Roman numeral to tell me the charge of lead here was +2, which meant I only needed 1 oxygen. But here it was +4, which told me I needed 2. Okay, so our other category of compounds are molecular compounds, and that name comes from the fact that they form molecules. So molecular compounds are 2 non-metals, so they're going to come totally from the right side of the periodic table. Another word for them are covalent, because they share electrons, meaning they form what we call covalent bonds. So naming molecular compounds is extremely easy, all right? And so is writing the formula. So we use prefixes. So our prefixes are going to tell us how many, not our charges. This is where people get confused. They start trying to balance 2 nonmetals. Guess what? They're both negative. You're never going to balance them, okay? So for ionic, we use our charges. For molecular, we do not. We simply use prefixes, okay? So for the examples given, carbon dioxide. There's no prefix in front of carbon, so it's 1. Di means 2, so CO2. Dinitrogen, pentoxide, di means 2, pent means 5, N2O5. So when naming them, we simply use those prefixes to indicate how many. So here are my prefixes: mono, di, tri, tetra, penta, hexa, septa, nona, and deca. Every element gets a prefix to indicate how many there are, except the first one with mono. I don't really know why this is the rule. I don't know if they thought starting the name of a compound with mono sounded weird. I have no idea. So, for example, CO is carbon, can't write, monoxide. So for the second one, we do use mono, but never for the first. Other than that, we always use a prefix, whether it be the first element or the second element, and we always, again, have to change our ending to "ide" because that indicates we have a compound. So no mono for the first one, carbon, there's 2 dioxide. 2 nitrogens, dinitrogen, 4 oxygens, tetroxide. So again, here's some practice for you. I would recommend that you pause it, do these on your own sheet of paper, and then play the video to see the answers. All right, here are your answers. Nothing tricky, just the thing to remember is that we don't use mono for the first one, but we would use it on the second. All right, finally, we have acids and hydrates. So we're going to start with acids. So we know that something is an acid when it starts with hydrogen, okay? So we're going to have 2 categories. We have binary acids where it's just hydrogen plus an element. So we're going to change hydrogen to hydro, and then we're going to change the ending of the nonmetal to ic, and then add acid. So HF becomes hydrofluoric acid. Another example, HCl would be hydrochloric acid. All right, then we have oxyacids, which really is going to be hydrogen plus a polyatomic ion, which is almost always going to have oxygen. That's why we call them oxyacids. So in this case, we're going to not use the prefix hydrogen. We're going to name the anion, and then we replace ate with ic and ite with os. Okay, so I like to remember this like I ate it, ate ic, and I have the itis, ite us. And then you name, you end with acid. So here, because it's hydrogen with a polyatomic rather than with a singular element, we are not going to use hydro, but we're going to begin the name of this, which is nitrate, but we're going to change that ate to ic acid, so nitric acid. So why do we have this weird rule? So let's say we had these 3 acids, H2S, H2SO3, H2SO4. Those are 3 completely different acids. And if we didn't have these rules, just me giving the name wouldn't be able to indicate to you which one of those. So instead, we have these rules that tell me, okay, well, this is hydrosulfuric acid. This is sulfurous acid. And then this is sulfuric acid. So our endings of, this beginning with hydro tells me it's just sulfur. No hydro and us told me it was sulfite. And no hydro with ic tells me that it's sulfate. So here are some more practice. These are just acids. So again, pause it, try it on your own, and then play it to see the answers. All right, so here are your answers to the acids. So our big things to remember is if we just have hydrogen with an element, like here, we use our prefix of hydro. If we have it with a polyatomic ion, we do not use hydro, and we change what is permanganate to ic acid, and what is nitrite to nitrous acid. All right, down here, carbonic acid, this ic tells me that this was with carbonate. Hydrophosphoric acid tells me it was just with phosphorus. And acetic acid tells me that this came from acetate, or that it is acetate. All right, finally, we have hydrates. And hydrates are just salts, which is another word in chemistry for ionic compound. And it is an ionic compound that has water molecules combined into its crystalline structure. All right, so we name the ionic compound like we name any other ionic compound that we learned how to do. And then we use a prefix with the word hydrate to tell me how many water molecules per formula unit of ionic compound. What I mean by formula unit is for every one CaCl, for example. So for every one calcium with 2 chlorines, there would be, in this example, 2 water molecules. So we just use those same prefixes. So this one told me dihydrate, meaning there were 2 waters. Writing the formula, write the ionic compound, a dot, the number of waters. That's it.